If you recall, this week has been about partial derivatives, how we calculate partial derivatives and how we think about partial derivatives. The good news is that it's the same kind of thinking that we had with derivatives in the past. dy dx is how much y is changing in the x direction. What happens to y when x increases by 1? Approximately, because 1 is kind of a big gap. But the same kind of thinking applies to partial derivatives. We have dz dx and dz dy. dz dx is how much z is changing in the y direction. So if we imagine a plane that's flat, dz dx will be how much we rotate that plane going in the x direction. And because we have a plane, we have another axis about which we could rotate our plane. So we have dz dy. How steep is the plane in the y direction? So this week we've attacked the notion of direction to derivative or slope. We have slope in a particular direction. How are things changing in a particular direction? Our two basic ones are dz dx and dz dy. And yesterday, we wanted to start thinking about derivative in any direction. Not just x and y, but some combination of x and y. So, to that end, we looked at a contour of a surface. Remember that the contour of a surface is going to be a curve at which all the values along the surface are the same. This is where z is equal to some constant value. And then the question that we asked was, we have a vector tangent to the contour. What will be the rate of change of function in a direction tangent to the contour? And how can we think about that? And then how will the mechanics work out? So does anybody have any ideas? How much does z change if we're moving tangent to the contour? Let's think about this way. If we're moving tangent to the contour, we can think about that as moving along the contour. So think about moving tangent to the contour as moving along the contour. So if we are moving along the contour, how much is our elevation changing? We're thinking about this contour as, say, the side of a hill. If we're walking along a contour, how much is our elevation changing? How much is z changing? We think of the contours as the contours. Imagine a topographical map. The topographical map has lines at different elevations. So in terms of a topographical map, we are walking along one of the contours. How much is our elevation changing if we're walking along the contour? So here is a line where the z value is all the same. So z is equal to k at this point. We walk along the contour a little bit. What's our z value here? Also k. What's our z value here? Also k. What's our z value here? K? K. Whole conversation, one letter. K. K? K. K. So how much did our z change when we're moving along the contour? 0. It didn't change at all. If we are moving tangent to the contour and we calculate the derivative in that direction, we should expect a value of 0 because our elevation is not changing at all. Z is constant on the contour. Oh, it's not 0 factorial. It's just 0. So there's a lot of stuff going on here. We want to think about the contour as being where z is constant. Moving tangent to the contour, that idea is that we are moving along the contour. Imagine if when we have a curve, we draw the tangent line. The slope of the tangent line is the direction that we're pointing at at every point on the curve. That's like where we're headed at every point on the curve. And that keeps changing as we cruise around the curve. So tangent is telling us about the direction of the curve. That's one of the big ideas what's going on here. Tangent is the direction of the curve. The defining characteristic of this contour, of a contour, is that the z value is all the same. That's where contours come from. This is a curve where all the z values are the same. So our derivative tangent to the contour should be 0 because we're moving along a path where the values of z aren't changing. This is just a question about direction, but the magnitude is going to be the magnitude will tell us how much z is changing. Remember, it's dz, dx, dz, and dy. If we have dz, I don't know how it's going to work. It's some vector, but this will be how much z will change if we move a small amount in the direction of v. The same interpretation as dz dx. How much does z change if we move a small amount in the direction x? So we are going to have to worry about magnitude at some point. We're going to want magnitude to be dropping out of this. So instead of a vector, any vector tangent to the contour, we might want to just consider a unit vector tangent to the contour. Good question about the magnitude. That is going to be a concern. But this is the idea that we need to have moving forward. When you're moving along a contour, when your direction vector is tangent to the contour, your z is not changing. That's the defining characteristic of the contour. It's where z is always constant. Tangents to the contour means no change in z. Where do you think we're going to have to go for maximum change in z? What do your just vector instincts, your calculus instincts, your physics instinct? Imagine yourself standing on a hill. You don't have to have calculations for this. You know that if you move tangents to the contour, you're just walking around the same elevation, going around the hill at the same elevation. How are you going to turn to go up the hill the steepest way? What is the steepest direction up the hill? Normal. It's exactly what you think it was. I freaking love it when math just behaves exactly like you think it should. Tangent is 0, maximum is at 90 degrees. And that's exactly what happens. Tangent is at 0, maximum change in z is normal to the contour. The maximum change in z will happen normal to the contour. Tangent is 0, perpendicular to that will be maximum. Now, if we're depending on which way we're going around the contour, if we're traveling tangent to the contour, it's 0 in either direction, right? If we're going to the left, no change. If we're going to the right, no change, because we're traveling along the contour. Now, if we imagine ourselves standing on the hill, perpendicular is going to be the steepest way up the hill. The opposite perpendicular will be the steepest way down the hill. We have two to choose from. Two to choose from. The steepest up, oh, I've already used red. So if we are perpendicular to tangent, that will be the steepest up depending on the direction of z, and the steepest going down will just be the opposite. Also perpendicular or normal to the contour. Any questions? We just have to look at which one is going in the, or which one is going towards the higher values of z. So there's going to be one contour here. This is where z is equal to 5. We look at the next contour where it says z is equal to 6. Going towards that one is the other. We've only got one contour, so we're kind of floating out in space with little direction. No change tangent to the contour, maximum change perpendicular to the contour. Yes, that's exactly what the next place that we're going to go. Now we're also going to have all this stuff in between. Look at all the stuff that we're identifying, all these different directions. We've got just in the x direction, just in the y direction, then we have a contour. Tangent is going to be no change. Perpendicular to that will be maximum change. And we're going to be interested in all the stuff in between. So what about the stuff in between? I love it when math class is super predictable. Which direction? If the 0 is tangent, which one is maximum? Normal to that. What about stuff in between? Great question. Let's talk about that next. It's perfect. I love this page, top 3. So this is the scenario we're dealing with. We're moving tangents. This is like a top view moving along some contour. Going tangent, traveling tangent to the contour means we're moving along the contour, which means our elevation is not changing. If we are walking along the hill, following the contour, and we want to go the steepest route up the hill, we will turn perpendicular to our path and go straight up the hill. All right. So what about the stuff in between? What about directions in between tangent and normal? So let's get a better idea about what's going on between tangent and normal. Tangent is 0. Normal is maximum. I'm going to cap the maximum at 1 because if it's going to be more than 1, we'll just multiply our way out of it. No one ever challenges that, so we're good. We're good. So instead of max, I'm just going to call this 1. And if it's 50, we'll just scale it up. So we're going to scale what can happen to be between 0 and 1. Now we're going to try to think of a function that has a maximum at 1. And then when we get to perpendicular, when we get to 90, we drop down to 0. What starts at 1 and drops down to 0 in 90 degrees? Cosine. And when we're dealing with vectors, what operation involves cosine? The dot product. That's what we're going to do. We're going to figure out what vector will give us maximum, call that 0 degrees. And then we'll do a dot product with any direction in between until we get to tangent at 90 degrees off of our maximum. And that will drop the cosine down to 0 because it'll be cosine of 90 is equal to 1. So maximum 1, because this will be cosine of 0 degrees. And tangent will be 0. And this will be cosine of 90 degrees. So if we could figure out what's going on at the normal, if we have a vector that's normal to our contours, we can find the dot product of some rando direction to find out how much our change is going to be in that direction. Oh, you mean like when we say degrees like that? I think it's just because we'll be like all, I was going to write 90. That's too hot for the Bay Area. How about 70? I think it's just because we just say degrees Fahrenheit. So I think you just write 70 degrees. Yeah. That'd be my guess. Yeah, we're 90 degrees, so we put the degree after the. I'm not really a fan of the degree symbol, but it's what we inherited. It's like radicals. We could really just kind of do away with radicals and just replace that with a 1/2 power. And then I think it would save a lot of algebraic kind of suffering when we start trying to compare radicals to exponents. Radicals are exponents, but we don't really view them as exponents because they look like radicals. We think there's all kind of weirdo different rules for it. And like a lot of the things that we needed in the past, like rationalizing denominators, so there's not radicals in the denominator, I think that's kind of gone away in the age of massive computing power. So I think radicals get in the way a lot. But we keep them for tradition. And tradition is just peer pressure from dead people. But they're dead people. Why are we worried about it? You know what I mean? Army of dark chocolate. All right. So if we can get a vector that's going to be normal to our contours at every point, then we want how much things are changing in some direction between normal and tangent. We can just take our normal vector, dot product, the direction that we're interested in, and that will be maximum at 0 degrees in the same direction as normal, and 0 when we get to tangent, because cosine goes from 1 down to 0 in 90 degrees. Any questions? Now, all this is to say, I'm going to write down how to calculate the direction in the derivative in the direction of a unit vector. And I could have led with this, but then we're doing the explanation at the end and people stop paying attention. I realize that most of you stop paying attention at this point, but at least this makes more sense in my mind to explain it this way. These are derivatives in a particular direction, so we cleverly call them directional derivatives. I love it when the names make sense. We don't come up with fancy names for things anymore. Do you know that when you have X coordinate and Y coordinate, like horizontal coordinate and vertical coordinate, one of them is called the abscissa and the other one is called the ordinate? Anybody know which one is which? Yeah, it's like X comma Y. Is X the abscissa or the ordinate, and Y the abscissa or the ordinate? Does anybody know? I don't either. That's how important it is. I wonder about it every other, like twice a year, times the number of classes. 6 times a year, I wonder which one is which. I never bothered to look it up. So I wonder how important it is right after. You know, in a subtraction problem, there's names for the terms. Like if you add stuff, like in 2 plus 3 equals 5, we know that 5 is called the sum. That's a common word. What are the 2 and 5 called? No. They're all numbers. A number that's involved in an addition is called an addend. Yeah. Who knows, right? We know sum. We know sum is the result of addition, but the pieces of the addition, usually we just call them terms, but they're called addends. There's name for things in subtraction too, like in 5 minus 3 equals 2. We know that 2 is called the difference between 5 and 2. What are the 5 and the 2? 5 and 3. What are the 5 and the 3 called? No, one is called the minuend, and the other one is called the subtrahend. Does anybody know which one is which? If I had to guess, that's what it would be, but I don't actually know. That's how important it is, because we just call them terms. I think back in the day, they didn't have Xboxes, so they sat around and came up with names for things until it got dark when they went to bed. Anyway, that's a tradition I think we should go back to. Well, it's dark outside, so it's time to go to bed. Be like, well, it's dark at 5 o'clock. It's also cold at 5 o'clock. So let's just go to sleep. Yep, in the morning. It's not going to be light until like 8. Okay. But school starts at 8. No, because it's still going to be dark. Let's just start school at 10. No one wants to listen to my idea. Like, everybody remember high school? How many of you had a high school that started at 8 o'clock? You know how bad that is for you when you're a teenager? To force you to get up early and go to work at 8 o'clock? It's physically bad for you. We have done permanent physical damage to you just by forcing you to go to school at 8 o'clock when you're a teenager, when you're an adolescent. We have fucked you up because of it. And people are like, oh, hey, you know what? Look at all this evidence, the scientific evidence that people are getting messed up when they're adolescents because we're making them get up early. Why don't we make them get up later and just start school later for them? And people are like, oh, but no, we've always done it this way. Tradition says do the damage to the young people and it's okay. Back in my day, this is because older generations are assholes. And they're like, well, I suffered, so everybody has to suffer now. Then they they clutch their pearls and get all offended when we're like, oh, shut up, boomer. Was that? It is people in general. Right now, like Gen Z is like, oh, we're not going to be that way. You will be. Right. Yeah. But there's like little progresses that get made all the time. Little tiny little progresses. It kind of sucks. If you're in a marginalized community, it's like, oh fuck, I guess I am born too early to be in this marginalized community. Hopefully in future generations we'll have this shit sorted out. Then we look around and it's like, oh shit, nope. Yeah, we haven't done that one yet. You know what I mean? Anyway. You don't think it'll happen to you, but it will. At some point, kids are going to be listening to your kids are going to listen to a new kind of music when they're teenagers, and you are going to hate it. And you're going to think music was good when I was a teenager. Music when you were a teenager was just as shit as when I was a teenager. So that's just the one that you attached to. You know what I mean? The important thing is that you recognize that it's just as bad as the music the kids are listening to, but they like it. So just get the fuck out of the way and let them enjoy that stuff. You know what I mean? Don't try to make them listen to Steely Dan. No one under the age of 1,000 wants to listen to Steely Dan. I mean, nobody. I mean, sure, there are things that we remember, like Bohemian Rhapsody and shit like that. That kind of stuff. There's some things that just transcend time. But go back and get the top 40 from when you were 14 and see if you remember, if anybody can recognize a majority of them. That's not in your age group. You're like, oh, who the hell was that? Who the hell was that? Who the hell was that? It's like, oh, they had a number one hit. I don't remember them. Do you know what I mean? Does anybody know who Paula Abdul is? How many people know Paula Abdul's music? Yeah.
Just the American
That
Idol.
album that she released, every single song on, I can't remember what the name of the album was. Every single song was a hit. There were no non-hits on that album. They're like, well, here's our first single, hit. Here's the next one, hit. Every single song. It's like you get an album and sometimes it's like, oh, there's 3 hits and then 4 kind of forgettable ones. Every single song, right at the top. And like 3 people are like, oh yeah, Paula Abdul. I can name a song because my mom wouldn't stop playing it in the car. What are we talking about? Directional derivative. We want the derivative of a function in the direction of a unit vector. I should write the notation for this. So our notation is very similar to the fx and fy notation. Fx is the derivative of f in the x direction with respect to x. Fy is the derivative of the function with respect to y. That's in the y direction. So FV is the derivative of f in the direction of unit vector v. This is how much the function is going to change if we go a little bit in that direction. And it is calculated with the dot product. That's the gradient of f dot the unit vector that we care about. Earlier, we had a question about the magnitude of that direction. That's why we want to use a unit vector. Unit vector just means the magnitude is 1, so we don't have to worry about it stretching or shrinking our dot product calculation. So what we're calculating, the direction is given by this unit vector, and we're going to take the magnitude of the gradient of f, multiplied by the magnitude of v, which is equal to 1, times the cosine of the angle between the gradient and the vector. So if that unit vector is in the same direction as the gradient, then cosine of 0 is equal to 1. And we get our maximum change. Our gradient will tell us how much the function will change normal to the contour. If our unit vector is tangent to the contour, then theta is going to be 90 and cosine of 90 is 0. So our change in function will be 0, just like we were thinking about it before. Now, you might notice that I have not told you what the gradient is. I don't like doing a whole section on gradient. I like to tell you why we care about gradients. So here it is. Gradient of f is the derivative with respect to x in the I direction and the derivative with respect to y in the j direction. Things to think about the gradient. This is how we build the gradient. The gradient is going to be perpendicular to the contour. And we have thought about that before. That's going to be the direction of maximum increase. So the gradient is perpendicular to the contours. And it'll be the direction of maximum increase. Gradient, how to find it, what it represents, why it makes sense in the context of what we're doing. We're imagining a function on which is a surface. We have these contours where the value of the function isn't changing. Tangent to those contours is going to be no change, so the derivative is equal to 0. Perpendicular to those contours is the direction of maximum increase. And in between those two, we use the dot product to see how much we want of the gradient. 100% in the direction of the gradients, 0% perpendicular. It only seems like it's a lot to remember because there's a lot to remember. You have to remember all of it, all the time. In perfect detail. No problem. All right, this is going to get you started in chapter 14. Chapter 14 is going to be much more rational and break this down into much smaller pieces. But this is where things are headed. This is what we're looking at. You have derivative in X direction, derivative in Y direction. We want to be able to know how much the function is changing in any direction. And we're going to get there by looking at the gradient. The gradient says where it's maximum, and dot product will give us how much of that maximum we're getting. All right, that's it for today. That's it for this week. I'll see y'all on Monday. Everybody have a good weekend, and thanks for playing.